Okay, welcome to the fields. Welcome to the AofA conference 2025. Steve, wherever is Steve, and me, Steve there, and me, are very happy that you make it here. And we also have some people online. I just want to very briefly say a couple of things. First, we want to acknowledge the Fields Institute for funding us and for providing this wonderful place for the talks. In addition to the Fields, we also have funding from the TIMSE, that is the TAT Institute for Mathematical Sciences from the Canadian government. And also we received some fund from Bob Sechovi from the Analytic Combinatorics book with Philippe Clajollet. So after that acknowledge of the money, I just want to say a couple of things. As you saw, the breakfast, the coffee break that for me will be breakfast, I guess, is here at 10:30 in the morning, also in the afternoon. And we also have lunches in the same place that will be, served different things every day to eat here and mingle around. So you don't need to really go somewhere else at noon. You can do it if you want. And if the weather is good, we normally open the door to the backyard there, so you can be outside. It's really a wonderful place to stay chatting with people and eating. In addition to that, we will have a Wednesday afternoon, some sort of excursion. The original plan was to go to the Toronto Islands. We need to, take a ferry boat there. And these are islands that are very nice to walk around, etc. But if the weather is not so good, raining, for example, then we probably will need to select something closer in a close place, likely a museum. There are some wonderful museums here in Toronto. So you probably on Tuesday will decide, and we'll ask you who is interested in going, because some people may decide to take the afternoon to work on a paper, whatever you want to do. Of course, you are free to do it. Okay. So, okay, I think that's all. There is one more thing. Thank you, Sebastian, for creating the link in Zurich. Many of you probably already saw it. If not, maybe we can send an email to the mailing list so you have it, the link exactly.
Just put it on the board. And
that's even better.
Get my drinks up here anyways.
So news will be posted there in case you want. We will also announce it here, of course. Thank you. All right. So I think, unless I forget something, did I forget something, Steve? I don't think so. If I forget, we can announce it again later in the afternoon. So I'm very pleased to introduce Sebastian Thiel from Germany now, and Liverpool at the same time, I guess. So Sebastian is very well known for many of us. He did this wonderful thesis that got a prize, an award for best computer science thesis, PhD thesis for Germany. What else? Austria and Switzerland. Germany, Austria, and Switzerland. That was our quick sort toward pivot. We have here talks about that. After that, of course, he came to Canada. He was very close to here at the Waterloo, working with Ian Munro. And then you got the position in Liverpool, etc. Now you are in Marburg, of course. So, and today you will talk about adaptive sorting and the like.
Thanks a lot for the.
Oh, you have yourself.
I have this one. Yeah, that's worth trying. Is that mic loud enough? Do you hear me? I don't know if the online people might, because it's a different mic. Okay, now everyone falls asleep, right?
Yeah. So I guess some people want to sleep here. So
boo! Wake up! Is it audible in the online meeting? Can someone confirm? I think you can hear me without the mic, but maybe.
I know. I think you need to use the mic actually. Sorry.
I'm trying to, but I don't know if that's close enough.
Someone said I guess we can hear you.
Okay, I guess it's good enough. Yeah, thanks for Daniel and Steve for the invitation to be here. It's a lovely place, and it's a great honor to open the conference. I counted that this is the 10th AofA I'm attending, with a little bit of cheating because there were the 2 online ones where it was very easy to get the counts. But I was part of this community for a long time. And so I was very, very ambitious with putting a lot of stuff into this talk and then cut it all out again because it was impossible to fit in the time. And I guess we don't have time until 1 p.m., but only till the lunch break, and you want to have some food. So I'll try to keep it reasonably short. There's some people in the audience where this work is based on. I'll refer to some other things with more people in the audience and beyond. And you'll see these pointers pop up. Before we dive into the actual topic, I thought I'll share a little bit of my other interests. Now, you've heard the story, so I don't have to tell that again. But I wanted to show my nicely hand-drawn university logos either way. And who knows what the next arc is going to be. I have 2 big interests that have some overlap, but I try to market them in this way that are a bit separate. One is very fashionable these days in algorithms is to say you're working on beyond worst case algorithms. It's a great definition because it defines the thing by saying what it not is. And that leaves you strategically a lot of freedom to put whatever you like under this umbrella. There's a few things here that I'm trying to get rid of this little thing here, maybe. No? Maybe at least I'm hiding it. That still works. There's the part about sorting algorithms that I'll talk about today. There's the part that is in the title, adaptive searching, that I cut out immediately. But if you're interested in what lazy search trees are, you can come and find me. And then there's also the question about models of computation, external memory for the algorithms experts. That changes the game further. My focus is really on very fundamental algorithms and data structures, and often making precise statements, which are exactly what this community is really good at. The second interest is in space-efficient computation, specifically storing things with very few bits, but so that you can still do operations on them. And specifically, graphs and trees are things that I'm interested in. For text, this is more or less known. That's a bit of a stretch, but one of these projects you will hear about on Thursday from Ziad, who is my student in Liverpool. He'll talk about these preferential attachment graphs. And there's many other variants of trees and graphs that we're interested in compressing, but working on still. If you're interested in that, that's great, but you will hear nothing more about this during this talk. But come and find me if you want to have a chat. I'll give a little bit of context, and then I have 3 little parts. The first 2 are really about quicksort and about the things that, as Daniel mentioned, were in my thesis to some extent, and then extensions. I'll try to keep those really short, though, and talk about this last bit a bit more, which I've never spoken about at any AofA before, although some of you may know. For the context, let me first define this part of the title, adaptive sorting, and forget about the searching. Adaptive means there's some sort of structure in the input beyond just its size n that we try to exploit. And for sorting, this can mean the input is in some sense already sorted or close to being sorted. Some examples are here on the slide, but you can invent any of your favorite ways of how the input could be closer to sorted than a random permutation. And then you can try to design algorithms whose comparison count adapts to this. Now, there's a lot of these known, but many are only up to a constant factor optimal. And what's more, they're not necessarily efficient in practice. I always imagine a conversation between sorting algorithms, some clever optimal adaptive algorithm that talks to quicksort. Now I know exactly what to do, and I'm going to sort this very, very fast. And quicksort says, oh, that's great. I'm already done. You have to do something with very low overhead. Otherwise, it's not going to be competitive in this case. That's adaptive sorting. The second bit is a shout out to Bob Sedgwick, I guess, among other people, and Conrado, who coined this term algorithm science a while ago. So you have to tell Bob when he arrived that he missed the joke. There's more jokes on him. So
I'm here.
Ah, you're online. Amazing. Good. So watch out for the other nasty comments later. This one's a friendly comment. There's a bit of a divide that maybe I'm overemphasizing here, but I think there's some truth to it. There's in computer science a community on systems engineering, which is building specific systems to be fast in an application. And then they do empirical tests to determine how fast is the specific algorithm on these specific inputs in my application, and maybe which algorithm is the better choice. And on the other hand, there's algorithm theory, which would be typically targeting theoretical computer science venues, where the whole focus is on worst case analysis and big O bounds, where we always have these hidden constants, which if you're strict, do not allow any prediction of specific running time on some concrete input. And algorithm science is this magic bridge that we're trying to build between those two worlds. And what we do concretely is the usual justification to do just big O bounds is that you're running on some machine that you don't know anything about. And so the exact constants will always depend on the precise machine. But you can count something more abstract, like we'll see examples in the context of sorting, counting, comparisons, and other things, which you can precisely count even if you don't know which machine you're running on. And you can go beyond the worst case, and you'll see examples in the context of adaptive sorting. And with these two things together, you can try to get what I termed platform-independent performance guarantees. So you can still make a concrete prediction on any specific machine, and you can validate these predictions by doing running time tests. That's a bit of the backdrop to some of the topics that will follow. And the specific examples that I picked happen to be from the Java library, although they're applicable beyond that. And some are also in other libraries. We'll come to that. Java is particularly useful as an example because it's open source. Everyone can look at what they implemented. But also, they have all new sorting algorithms. And both of them happen to be introduced in 2009. Don't ask me why that year was so special. And were two independent efforts. There's two methods in Java. One is for primitive objects, essentially integers and floating point numbers. And the other is for sorting objects that can have a complicated comparison function that is defined by the users. In both cases, these came from developers, and their focus really was on empirical performance, maybe unit tests to check that the sorting algorithm correctly sorts, but not normally proofs or mathematical analysis. Let me give you a very brief recap of what happened on the left side in this previous slide on the dual pivot quicksort that is implemented in Java. First of all, why would you even change a well-running implementation in a standard library? Simply because the new version was way faster. Now you have to be careful here. I cut the y-axis, so it's a speed up from 7 to 9 roughly, but that's still a significant speed up. So it's a great case study for algorithm science because at the time they introduced this new method without knowing why this was faster. They did tests. It was convincingly faster across many different types of inputs. So why would you not use it? But it wasn't clear what the reason behind it was. So making a long story short, you can invent different cost measures. The classic one would be counting the number of comparisons. And you can compare those two methods. And indeed, you see this new dual pivot quicksort is performing a few comparisons less than the other one. So that sounds like a great explanation. Now, a little aside for the experts, you may note that these numbers are not what you would recognize as the typical numbers for quicksort. And that's because I chose the pivots in a specific way, mimicking what happens in the library for this one. And then for standard quicksort, mimicking pivots of the same quality as what we get here. There's something I don't want to go into further detail, but the point is that we're looking just at the leading order term, and I'm ignoring the linear term, which is hard to compute in a precise way. And then you want to adjust in this way to have a fair comparison. For the big picture story, so wake up everyone else, you can ignore this part of the aside story. The comparisons seem to indicate there's something going on, but then if you look at other kinds of ways to quantify computational effort, this doesn't look so good for this new sorting algorithm, except for the very last column or row, which is essentially the number of element transfers from main memory to CPU. And there you see a substantial improvement. And for the algorithms people in hindsight, this is not very surprising because by using 2 pivots at a time, you get more work done in one pass over the data. So the main thing you can save on are these memory transfers. But by looking at all the other measures, we can kind of rule out that they have an influence because they all don't look very convincing. Only memory accesses show a benefit for this faster method. And that also answers a related question that people would probably have at this point. Why did nobody do this earlier? I think this year we're celebrating 50 years of your PhD thesis, Bob. And there was a dual pivot algorithm in there too, but it wasn't faster at the time. And even much later when the C library was designed, it wasn't faster at the time. It's just a changing of the relative weights of cost in the CPU and memory transfers that makes different algorithms favorable now. And this is a nice showcase for algorithm science because it gives you a very clear understanding of what happens in the background. A little remark that I put in my thesis a lot of work on the general case, more than 2 pivots. I never ended up publishing this as a paper outside of the thesis, so you really have to look at this book if you want to read about it. You can essentially generalize the full analysis for any number of pivots and any sensible ways to generalize these partitioning methods. And there's a few special cases that you can recover in the analysis that gives you, as a special case, the results that were known for these particular variants. Okay. The lesson you learned from this is similar. In terms of comparisons, it doesn't help a lot to have several pivots. For scanned elements, essentially these memory transfers, it helps. And there's probably some sweet spot for a reasonable number of pivots, just because some things become more complicated if you go crazy with a huge number of pivots. So a quick summary, we've not seen the details of this asymmetry, but that's something some people may remember. The only optimization that gives you these memory transfers is multi-way partitioning. So that's really something worth doing there. And I want to mention, as throughout the talk, a few open problems that I think are still, from a computer science perspective, very worth solving. I would like to know the answer, but it seems all the approaches I know are inconvenient to do this. Determining the linear term of costs. Sorting algorithms like quicksort have an n log n leading term, but then the linear term is not that far away. But for those, you need to specify the full algorithm. There's no very convenient way. Maybe there's a way to automate some parts of that. So I'll try to make an effort to point out open problems from all these stories. And maybe someone finds these interesting. I'm happy to tell you more about that offline. There was a lot more with various people in the audience in some cases. Another open problem in this quick XORed that I think is not solved yet. A lot more to tell, but not today. Any questions about this dual pivot quicksort part? This was a fairly old story. It's not 10 years, not 50 years ago, but approaching 9 years for some of it.
I have a question.
Yeah.
Can you at least get the B order term for the variance of the?
For this one?
Yeah.
In principle, yes. It's a long recurrence. And I remember sitting in some place in Uppsala and working on this, and then I kind of gave up at some point because it was too much to do on paper. But it's very doable.
Will it still be standard deviation of order 10?
I don't want to say anything wrong. Not sure. The recurrence is a bit different, so it is not clear. It's not obvious, maybe. Okay. Other questions on dual pivot quicksort? Then we briefly stay with quicksort for a bit. So far, there was nothing adaptive about quicksort. Adaptive, again, meant exploiting pre-sortedness in the input. And indeed, if you assume random permutations, then we know a lot about this algorithm in all its variants. And many people in this room have worked on this, and we have a very good understanding of the performance characteristics. But effectively, if you give up random permutations and have inputs where there are some elements equal to each other, then it's essentially a comprehensive list of literature here on the right, 5 papers plus the one I'm telling you about. So there's an indication that maybe there's a bit more attention useful to this part. So the justification for random permutations usually is in quicksort that you want to randomize or pick a random pivot anyways. The algorithm has this quadratic worst case, but by randomization, you can take this worst case input and turn it into an astronomically unlikely event that you're just never going to see in real life. But equal keys won't go away if you shuffle, right? They will stay. And the good news is that quicksort actually can exploit equal keys. It gets faster the more equal keys there are. If you're slightly careful with it, that's at least true. And it might be one of the reasons why it is so popular in some libraries. Beyond just being fast on average, it also can handle with this this frequent case very well. Let me define a little bit here what we mean by having some equal keys. You can define this in many ways, but there's 2 models that were studied. One is you have a multi-set of numbers. So you can take numbers from the universe 1 up to u, the integers. But you can have each of those a certain number of times, and you fix this. So I'm telling you there's exactly x1 once in your input. But then this multi-set is randomly shuffled. The other option, that was maybe one is the combinatorial point of view, and the other is the stochastic point of view or probabilistic point of view. These keys come from a distribution. The distribution is over a discrete universe. So you expect to see duplicates if the universe is small enough, but you don't fix exactly how many duplicates, you just fix the probabilities for the different numbers in the universe. And of course, we know these models are not terribly far apart under some constraints, but these were in principle 2 different models. So the connection, of course, is that here these the number of occurrences is a multinomial distributed random variable, whereas here it was a fixed parameter. If you want Quicksort to optimally exploit these equal keys, you have to get rid of them whenever you partition. And that's often termed fat pivot partitioning, which I think is a very lovely term to describe what happens. You just partition into three segments, strictly smaller and strictly larger, and what's equal in the middle collects all the pivot occurrences. So they're gone after one such partitioning step. It also has the benefit for the analysis that we do get a recurrence where we have the same kind of distribution or same kind of inputs in the recursive calls. It's not impossible to work around that if that doesn't happen, but many of you will know that this is a pain, and this makes life much easier. And in terms of the cost model, I'm assuming that we have ternary comparisons. So one operation that tells you whether two elements compare less or equal, greater, equal, or equal. Strictly greater, strictly less, or equal. And on top of that, to make things interesting, we're picking pivots in Quicksort in the usual way as it's done in practice, namely from a small sample of 2t plus 1 elements. Think of t as a fixed constant. Often it might even be 1, so you pick the median of 3 elements. But because you skew your pivot to be away from the extremal ranks, this partitions on average substantially more evenly than if you were to pick a random pivot. And so this is a common choice in practice because it doesn't cost a lot to sort these 2t plus 1 elements or pick the median from there, but it gives you a substantial benefit. You could also do this asymmetrically, but we're not going to do it today. Question?
Are you something with or without replacement?
For this model?
For the median of 2t plus 1.
I guess these are taken out from the partitioning. So yeah, you take the first so and so many, and only the others are partitioned. Now, if you don't do this pivot sampling or set t to 0, then Bob had a talk at the Knuth Fest about the analysis, which fits on 3 slides. I'm not giving you a chance to read it. I just want to make the point. It's a fairly concise analysis. It's a beautiful trick where you subtract certain terms in the recurrence. Maybe you can just see this part here. And then it magically works out to give you a nice term that you can bound in terms of the Shannon entropy of these numbers normalized. It's a very beautiful analysis with a clever trick that does not at all seem to generalize beyond this case of picking a random pivot. As soon as you start saying, let's take the median of 3 elements, all of this somehow falls apart. And that was all there was. We didn't know how to generalize, but the talk had this conjecture that if you increase the sample size, then the cost of Quicksort would converge to the optimal cost, where h here is this entropy. You take the xi, divide them by n, so they become probabilities, and then there you can define the entropy. And that's the information theory lower bound. If you determine how many different permutations there are of such a multiset, that's exactly a log of that number. And so I'm going to show you that you can settle this. I'm going to show you the high-level picture of this, but with some restrictions. And lifting those restrictions is another problem that I would like to propose. So for that, we need a little correspondence between Quicksort and binary search trees. It's a known trick that the recursion tree of Quicksort, the pivots, and then the left and right recursive call, again with their pivots, this forms a tree, a binary tree. And that is effectively the same as if you were to build a binary search tree without any rotations or balancing. by inserting the elements one after the other into a binary search tree. And so the comparisons that Quicksort needs are the same as the comparisons needed to build this binary search tree. And that's known or fairly standard if you don't have any duplicates. I'm going to show you by proof by picture example that the same works if you have duplicates. So here's an input for Quicksort. And we're picking the first element as pivot. I'll come to the generalization later. So you remove all the occurrences of 4, right? These were here in the middle, but then you have the smaller and larger elements separated out. And you recursively do the same in this part. And you connect the pivots as they were called left and right. So that gives you a binary search tree because everything here left of the 4 has to be smaller, so it has the search tree property. If you were instead to build the binary search tree by insertions, this would look as follows. You start with the 4, that becomes the root. And then 2 is smaller, so it has to go to the left subtree and stays there. 1 goes further left and becomes a new leaf, and so on and so forth. And if you have an element that's already in the tree, like this second 3, you follow the search path to that element, and you just determine it's already there. I don't have to insert it again. But you're paying the same comparisons as if you were to search it again, because you have to find out that it's already in the tree. So if you do this, there's one more that makes a change, but then the others are really just searches in the tree that don't change the shape further. Okay. One more thing is we want this really with pivot sampling. This was with a random pivot. What do you do if you have, say, the median of 5 elements? So here's an example of what Quicksort looks like with this. You find the first 5 elements that might also answer Conrado's question in the end. You find a median element in this list, that's 3. So you use that as your pivot and you partition the others left and right. Now, I don't separate out the ones that were in the sample, but they're part of the recursive call. But they wouldn't pay for the comparisons there. Now, if it's small enough, so if I want to pick the median of 5 elements, but I have less than 5 elements, I'm just saying there's some other way to sort those. Some base case of the recursion. And same here, I get another degenerate partitioning step with the left and right basically empty. So I get this tree. And note that I'm just leaving in the leaves these elements unsorted because they're dealt with somehow separately. I can emulate the same thing in a tree as follows. I have leaves that can hold up to 5 elements, and as long as there's space, I'm just filling that. If I try to insert another element, I have to flush this first. And at this point, when the leaf is full, I'm finding the median of that leaf. That's the 3. And then it splices out a new internal node and generates 2 new leaves. That's equivalent to other forms of describing these fringe balanced trees. They have also been around for a long time. That's an easy way to draw them. It does the same as modifying fringe subtrees. Then we keep on inserting. Again, it's a binary search tree. The 5 is bigger than 3, so it has to go here. There's space in the leaf, so you just put it in there. And that goes on for a while. If I find an element that's already in the tree in an internal node, then I just note it's a duplicate and I don't change the tree. Whereas the leaves are happy to collect several duplicates of the same value. That's important. Okay, one more, then this also splits. And we have another search for 2, which, because it's a leaf, ends up here. And then again, you see the 2 trees are the same. So you can generalize this correspondence between binary search trees and quicksort executions to duplicate elements and to sampling pivots from a small sample. I guess that's the main part to take from this. So what this means is, if we want to analyze quicksort on inputs with equal keys, we might as well analyze what it takes to build this tree or what it takes to search in the final tree. This is something you can observe. I had it on the slide before. Okay, that's not going to go back all the animation. Building the tree is the same comparison as searching all the elements in the final tree if it was already given, just because an insertion does the same search path as a search in the final tree. So we can analyze trees instead of quicksort. If you do that, what will happen after a while is that the tree is fixed and then you only see duplicates. Maybe it only happens at the very last step, but it might happen much earlier. In particular, if your universe is not so big. So here's an example where we just have 5 different keys, but it's a longer list. If you start building this, this tree, then for a while it changes. Whenever there's a duplicate key, it doesn't change. But then from this time on, I've seen all the 5 different keys, and the search tree will not change from there on. It will only be used for searching these elements. And so I should be able to exploit that this is very regular on the right. The picture again showed just the case with random pivots, but if you use these fringe balance trees, it's the same game. They also don't change after some point, because once everything is in an internal node, they're stationary as well. So we can split the inputs and think of this process of 2 parts, consisting of 2 parts. The first is growing a tree, and then the second part, the tree is stationary, and we just search in the tree. Now, if this prefix where we build the tree is very short, then we can maybe get away with just ignoring the cost of this part entirely. And the reason I'm doing this is because it's very hard to analyze precisely. The second part then, where the bulk of the cost hopefully comes from, is very regular. I'm just searching in a fixed tree, and that might be easier to analyze. Now, if you think about the 2 models that we had, then here is clearly the model with a fixed profile, not as convenient as the other. Because if I pick each element uniformly at random, independent of all the other elements, the input of the second part here is independent of the prefix of the input, and hence independent of the shape of the tree. If I stick with the combinatorial model, this is much less convenient. You get some dependence there, and it's not clear how to handle it. But if you use this random model, and we can somehow show that this prefix is not too long, where the tree is still modified, then we're in good shape. And that's essentially the analysis. I'm not showing you the detailed computations. So it's just these 2 pieces that you have to establish. There's a separation theorem, which I showed you by example how this might work. In detail, what it needs is that this universe size is not too, essentially you pick U so that even the least frequent element occurs a polynomial number of times, and to some epsilon. Then you can imagine you don't need a lot of elements before you've seen everything at least a few times, and then the tree is stationary. So that theorem just says that this picture from the previous slide indeed works if all the elements occur often enough. And then the hard work is analyzing what does the tree look like if you randomly build it that way. And that's indeed a bit of a tour de force by just studying a recurrence. You can observe that the entropy of this search tree has the same shape as search costs, and then you can exploit the properties of the entropy to get a recurrence. But this is nowhere near the elegance of the analysis for picking a random pivot. Okay, then with those 2 things, you get the claimed statement and the proof of this conjecture under the assumption that every element occurs often enough. Then that was the assumption. Then the cost to search in this random tree is given by the entropy of the distribution. So the entropy of the distribution you pick for the input, with a constant factor in front that depends only on how many elements you pick to sample the pivot. And you have an error term that is lower order term if the entropy is not too small. So it's a partial answer to this conjecture. We do get, if k becomes bigger and bigger, we converge to the optimal cost for this sorting of a multiset. But it has this asterisk to it that you need many duplicates. You can extend, if the input distribution is uniform, you can get slightly stronger bounds, and you can generalize to further variance of quicksort. But what's still open is how to get rid of this assumption that every element occurs many times. And it feels maybe you can push this a bit further, or maybe there's a way to get back to the combinatorial model and just avoid somehow to deal with this dependence of building the tree and then searching in the tree in a clever way. Questions on the part about quicksort with equal keys? This was supposed to be the technical part with a few scary math slides that every AofA talk should have. The last part is a bit more easygoing and storytelling like. If you don't have questions, then let's do stories. And there's a tiny bit of an analysis at the end, if we have time for it. So far, this was all about quicksorts, and this was all relatively old stories. The last part is about power sorts, a variant of merge sort that is used in the Python standard library now. And for that, let's start basic and slow again. What is sorting after all? And specifically, what is stable sorting? This is maybe a bit of even for computer science students, something that they may or may not see in some undergrad modules, depending who stresses it. The idea is simple. If we have a list of names and we first sort them by first name and then by last name, it could be a reasonable assumption that then afterwards the list is sorted in the usual way, first by last name and then by first name among those with the same last name. But for this second step here, when you sort by first name after sorting by last name, you require that you use a stable sorting algorithm, namely one where elements that compare equal stay in the same relative order that they had in the input. If you don't have a stable method, in this case, then what you end up with is sorted by first name, but not by last name. And it could be sorted by last name, but is sorted by first name, but not by last name. You lose the grouping. Okay. Is that the wrong way around? Yeah, you sort by first name and then you sort by last name. In this step, you need the stable sorting method. I was just pointing to the wrong panel. The slide is correct. Ignore what I said. So this is a fairly widely spread assumption that people that use sorting algorithms have, that it's a stable method. And so it popped up in practice as a requirement. Let me comment a bit about this Python and C Python and all these things. Python is essentially just a specification for a programming language. It's not a program. Then there's C Python, which is a reference implementation of that specification. So it's a specific program written in C. That's why it's called C Python, that implements this specification. And there's other versions out there that implement this Python language, but that's the most widely used. And it started out with essentially using what the C library had for sorting, which is a non-stable quicksort. Then Tim Peters, a name that will pop up again, found a slightly faster way, but still based on quicksort. So it still was not a stable method. And at the time when Python was becoming more widespread, more and more people using the language complained that it's inconvenient that the sorting is not stable. they were expecting this first name, last name trick to work, and it didn't work. And so they were annoyed. And so they at some point demanded, let's just make it stable. And then quicksort had to go, because with quicksort, it's hard to make things stable. So instead, it's now using a custom merge sort variant that was developed specifically for Python by Tim Peters and acquired the name TimSort. And that remained essentially unchanged for 20 years, and people were moderately happy. And we'll come back to that. And then there was an update a few years ago to replace one part of TimSort with PowerSort. And I'll tell you why that came about. Taking a quick step back, something I said already, but maybe just to make that clear again, there's two key algorithms that every student learns about sorting, quicksort and merge sort, and they have these 2 out of 3 desirable properties each. And combining them all 3 is a bit tricky. So you can be generally fast and in place, but non-stable, or you can be fast and stable, but need extra space. And sometimes you can't easily get all 3 of a desirable triangle. But because Python has a lot of objects, everything's an object, even an integer is an object. This extra space requirement was not so strong. So they use extra space already, so that the sorting algorithm would also need a bit of extra space. It was a reasonable trade-off. So that's why it uses merge sort. And in case you needed a reminder what merge sort is, here's a shout out to this IDEA instructions. They have many more algorithms shown in that way. So merge sort, in the normal way how we teach it, is it cuts in the middle and recursively sorts the left half and then the right half. And when you come back, you have to merge those 2 halves, and then you get a sorted list. That, however, is not how TimSort in the CPython library works. It takes this idea of merging or merging-based sorting and modifies it in several ways. And I'll comment on the joke with Tim Hortons in a second. First of all, it detects runs in the input. A run is just a consecutive piece in the input that is already in order, either increasing or decreasing. And if you think about merging, you establish segments in this array that are sorted, and then you merge them further to make these runs bigger and bigger. It would be wasteful to destroy runs that already exist in your array when you get started. But then if you do that, you need a way to decide which runs that you found you merge in what order. And I'll show you examples later why that's important. But just superficially, it's clear that once you found runs, you have to decide what to do with them. What TimSort then on top of that does is it tries to minimize the extra effort we need to do to keep those runs. In particular, it avoids first detecting all runs and then working with them. There's 2 other things that it does that Vincent knows much more about. In this case, for example, the merging is done in a more clever way with exponential searches. And in Waterloo, this was always known as Tim Hortons search, because you double the jump size in jumping. And so you can order the Canadian iconic coffee if you want, if you're up for a lot of sugar. And there's a twist to enforce a certain minimum run length that we're going to ignore. I just want to point out that TimSort has a lot of modifications to merge sorts, but I'll focus on a specific one here, which is the one that got modified with PowerSort. I have to explain very briefly what TimSort works like. I'm not expecting you to read the Python code there. But if you think about normal merge sort with this top-down recursive structure, forget about all of that. Instead, we're walking left to right through the input, and then we detect one more run, throw that on a to-do list that we have to eventually get to. That's this stack of runs here. And then there's a rule that decides, shall we do some work now, or do we postpone that for later? And these are these rules here that depend on the lengths of the runs on this stack. And I'm always just looking at the topmost few of them. And for example, one rule says if the topmost run is longer than the third, you should merge the second and the third, and so on. And you have to check those rules one after the other. Now, again, Vincent has a better intuition about this than me, but I always found these relatively unintuitive. The goal with these was to ensure that the lengths of these runs on the stack grow like Fibonacci numbers, so that whenever you go down, a run would be at least as big as the two above it combined. If you establish that, then you have an exponential growth on the run lengths, so the stack cannot be too tall, and that's convenient for various reasons. Why exactly these rules here? That's less clear, and Tim Peters publicly confessed it was the first thing he randomly tried out things, and that was the first that seemed to work okay-ish. There was not much more deliberation. That came only much later and was a lengthy paper in itself. But remember this invariant Fibonacci numbers, growing like Fibonacci numbers in the stack? It turned out this invariant wasn't actually true with these rules. In a very, very intricate pattern of run lengths, it was violated. And this was found out when people tried to formally verify that Tim sort is correct. It didn't come up before, or people didn't spot this mistake. But this was a nice showcase where formal verification showed an algorithmic bug in a widely used library. Again, there's people in this room that had some part to play in this, in fixing twice this bug. But I'll cut the story short there. In a way, what you have to do is add another rule and go one level deeper in the stack, and then you can guarantee that this invariant is really an invariant. Now, it's a sorting algorithm. It would be lovely if at least the worst case is an n log n comparison bound. And that is true, but it was very hard to prove from my perspective. I think this is, for a sorting algorithm, is a sign that something's a bit broken. If you need a sophisticated paper and a sophisticated analysis to prove even that the worst case is n log n, okay, first indication. Let's take a step back what the problem is that we're trying to solve here. I mentioned this earlier, that when we detect runs, we have to somehow decide when and how we merge runs. And so this is what conceptually happens. You find the runs, and then you decide one after the other which to merge. And you can restrict this a bit here to always have two runs, and they have to be adjacent, otherwise you give up stability. So what we're really doing is finding a binary tree called a merge tree. So again, a picture to illustrate, you find the runs in the input, in the example, just increasing runs. And then you have to somehow decide which ones to merge. Maybe you start with those two. The result is then a run of the combined size. And then you keep going. You can always take resulting runs and merge those further, or maybe you merge two of the original runs. Anything goes, and the result is a binary tree. Turn that around. Every possible binary tree is a valid merge policy. You could have taken any binary tree over these initial runs. So the merge policy is an algorithm to choose which tree to take. Now, how good is a tree? That depends on the merge cost, which is the length of all those intermediate results. And you can think about, you have to write those. There's also an upper bound for the number of comparisons. So it's a reasonable cost measure here. Just to convince you, here's two examples with the same runs, but then different merge policies, different trees on top, and their total cost can be very different. It's maybe not very surprising, but just to make that case very explicit. So what does TimSort do? Most of the time, if you run these four intricate rules and you check what the resulting tree is, it works okay. But sometimes, like in this case, it's an input with run lengths 1, 2, and 3, or multiples thereof, and a specific pattern. It does something awkward. Time and again, it merges a long run and adds a tiny little extra run into it. So it pays all the cost for moving this long run another time and making it tiny, tiny bit longer. And the same runs you can merge much more efficiently with a different tree. That's, for example, this one on the slide. And if you make the input bigger and bigger, the overhead that TimSort pays is 50%. That seems to be the worst that can happen, but it's quite a lot. And so at this point, that reminded me of an old software engineering saying, if you're riding a dead horse, get off. That's usually referred to some software architecture or hardware or so on. But maybe we should get off this, this merge policy in this case. Okay. For the rest, I'm going to speed up a little bit. We have the merge trees. If you rewrite the cost, it's effectively the same as a weighted external path length, because you, in this sum of the areas, you sum every element in the leaf as many times as it occurs in intermediate results above. That's just the depth. So you take the number of elements in the leaf and multiply that with the depth, sum that up over all leaves. That's what we call what we know as weighted external path length. And that's a well-studied quantity. Indeed, that's exactly what you optimize when you find optimal binary search trees. For those that teach algorithms, it's often a problem that one picks as example for dynamic programming or competitive programming. People know this as a example for dynamic programming. This is a well-studied problem, and we can inherit what people have proven about it already. For example, you can get a lower bound of h times n, where h, again, is something of an entropy form. You have to take the lengths of the runs and normalize them. And you can also compute the optimal such tree. You could take the optimal tree, but that's a quadratic or even cubic time algorithm if you don't take Knuth's trick. That's a bit slow. We're trying to sort. Remember, we don't want to spend n squared time figuring out the best way to order the runs. You could do a different tree, namely, if you think about these weighted path lengths, you could take a Huffman tree, and that's the best possible tree. And that idea indeed has been rediscovered 5 times independently. And only recently, the oldest source only recently was pointed out to me. So people had this idea a few times before, but it's actually not a solution in our case because it doesn't give a stable sorting algorithm. Huffman's algorithm combines leaves that are not necessarily adjacent. A little less known is the algorithm to find optimal trees where you only combine adjacent leaves. That's doable, but it's complicated. More realistic is nearly optimal trees, where you give up that it's the precise exact optimal. You just want it to have a good bound on the cost. And that's what ends up working. You get a bound of h plus 2, where the lower bound would have been h. So it's very close. And these are simple linear time methods, much faster than any of the other suggestions there. Okay. I'm going to give you just a rough idea of which method we pick there, and then maybe leave it with that. The idea that we use is a known algorithm that we then modify. And it's a simple recursive algorithm. You take your runs, you find the middle point that you would have if you just jump to the middle, but you don't want to cut there because then you would divide a run into 2. So you find the closest boundary between runs, and that's the point where you cut. And effectively, you recursively do the same. The only twist is you keep cutting the original interval in half. So you're not taking the left recursive call and go to the middle of that, but you go to the global list and take the 1/4 mark on this level. And that little twist is important because it means that these cut points don't depend on the recursion. They're predetermined. These are just regular cut points. Okay, a way to visualize this is imagining a complete binary tree, and you let the connections between the middles of the runs sink down like a pole, and then they get stuck on one of those parts of the balanced tree. That's doing the same as the previous slide in a recursive way. And that's the tree you pick for merging. And again, here the trick is really that this computation is local. All you need to know is where your two runs are. Then you can find the middle points and can let this blue line sink down. It doesn't depend on all the other runs in the input. So you can do this as a local computation. Okay. I'm going to skip the part that turns this into an algorithm. You can watch this in the PyCon talk if you're interested. And here would be the analysis, but I think I'm running out of time. So I'll skip the analysis in this case. Let me just say that this is all. Like the analysis that you get this h+2 upper bound is not even a slide, it's half a slide. It's a very simple algorithm. And I'm not trying to put you here to impress you with the analysis there. The point is that the algorithm is so clean and simple that the analysis is really boring. It's easy to state. Okay, let me wrap up here. TimSort is still, whenever you need a stable method, seems to be the method of choice in practice. The original version had this kind of strange merge policy that didn't quite live up to the standard, but that's easy to fix. And it's known by now. And it's fixed in some of the implementations, in particular, the one in Python. A bonus you get from this way of looking at the problem is that you can generalize it to multi-way merging. If you remember the dual pivot quicksort part, then you might imagine why that might be helpful if memory bandwidth is more your concern than comparisons. And there's a few open problems. In particular, can we think about a clean probabilistic model for inputs with runs? That seems to be, there's no convincing thing that I know of, but there's these mallows distributions for permutations and so on. Maybe something can be done for runs that has a similar flavor and allows a clean analysis. All we have so far is kind of a worst case analysis. We fix the run lengths, but then it's worst case over what happens once the run lengths are fixed. This policy I only briefly mentioned that you ensure that every run you find has a certain minimum length is not well understood. And I think it's not the best way to go about it. That's also not, there's more analysis needed there. And of course, we want this to be used in other libraries, but we're working on that. Let me finish with saying that I'm currently recruiting for 2 postdoc positions. So if someone knows anyone or feels they want to spend some time in Marburg, then talk to me. Thanks.